everybody. My name is Raouf Hadad. I'm with CSE Industries. We are system integrators in Houston, and our focus is on the upstream oil and gas and mainly in the offshore industry. And what I'm going to do today is I'm going to talk to you guys. I'm going to give you a little bit of a background about Subsea Topside Interface and give you a project example of how historically we operated these interfaces. And I'm going to talk about the MDS work group, which is the GIP that the industry decided that it was time to do. And I'll talk to you a bit about what we did there. And then finally, I'm going to give you one of our project examples where it's actually success story in the making. I was hoping we could say it's already done, but it's in development. But we already see some of the fruits of the JIP and the standard that we established. And I have a plane to catch afterwards, but my buddy Paul is going to cover afterwards if you guys have any questions. So I know we want to save the questions to the end. So a bit of background, and mainly for people who are not in the oil industry. Subsea to topside interface historically has always been very challenging, and for multiple reasons. I mean, if you look at this picture, what I wanted to do with this picture is to let you look at, on a platform, on topsides, there's usually the people doing the DCS, controlling all the process equipment on topsides. They have their hands full. There's usually, for a deep water facility, average is probably 4,000 plus instruments that are tied into their process control and safety system, in addition to tens of soft interfaces that they have to bring into the system. And one of them is the subsea control system, and that's called the MCS, is the controller that interfaces with all that subsea infrastructure. So if you look at the picture here, you'll see some subsea equipment there. This is all it's called the Christmas tree, which sits on the well, and some manifolds. Now what you see here is probably maybe 10, 12 wells. Typically on a very large facility, you could have these like on the north side and southeast side, things like that. So you could have some facilities up to 40 plus, 50 plus. The largest we had done is like 54 wells ourselves so far. So one of the things about W Industries is as system integrators, we had worked on both sides. We have worked with subsea equipment vendors where we delivered the master control station. And by the same token, we had worked with operators where we basically delivered the topside, DCS, process control, the complete system on topside. So we've seen the challenges from both sides. And what's so challenging, like I said, for the topside was basically the integration of the subsea application into the topsides. And again, other than the complexity and the amount of data that's involved in a subsea control system versus one of the other package units like instrument air or diesel generators or emergency generators, these systems are typically, they have a standard control. So basically, once they're given a PO, within a couple of months or so, they can give the topside contractor, like, hey, this is our data map. You need to monitor these 100 points. These are alarms, whatever. So it's very simple and cookie cutter. It gets passed around. And but the biggest interface is the subsea system, which could be in tens of thousands of I/O points that has to be passed and copied into the topsides. And the development time, the timeline for doing this. So this is showing timelines. On top is the typical milestones for a topside facility and everything that they need to do, all the way from the engineering and system architecture, start programming, building the hardware, do some unit level testing, some basic things on the third-party interfaces, all the way into your FATs. And what you see is like they happen in parallel. And you have a small window, and this is basically where it gets handed over to the topsides contractor. So you have very little time to integrate everything, get all the details in. So just historically, it was very challenging and always seemed to be troublesome, where in many cases, if things weren't caught early, then it may result in re-engineering. I mean, I'm talking adding more hardware or add additional cost and schedule delay, which I'll bring up in the project example I give. So this is just a typical system architecture for a topside system. And you'll see, so if I'm building the topsides, basically you see, the process control, safety, fire and gas, et cetera. You have all the networking that you have to worry about. And then the circled piece, that's the subsea interface. So again, so when things were missed in some of these interfaces, it's not because the topside contractor didn't pay attention. They just have so much on their plate. And if any small thing could result in a huge setback to the project. So I'm going to give you guys a project example, elaborate more on the challenges that we used to have. So there was a project, and it was in West Africa, and it was a very, very large system. And in this case, we were actually responsible for the subsea control system, for the MCS. And we had a spec given, and see what used to determine the interface and how to do things is depending on who's the engineering company involved and who is the subsea equipment vendor. And it was a combination of these two that basically drove how we build the system. So this project, it was basically said, okay, we want Modbus for critical data and we want OPCDA for the rest of the data. And then we're told, you got to be bit compliant. If you start asking any questions, hey, can we interface with the DCS folks and see if we can, change it to something else? Or like, no, just bit compliant. And that's what you have to do, see if you want. So that's what we basically started with. And even the Modbus, it used to be Modbus RTU at the beginning. So that's one of the first things we talked them into after we got the order was like, can we do Modbus TCP? We both do it, and it's a little bit faster. And so that's basically the system was based on these two protocols to bring the data in. And this is a very large facility. This is the biggest producer for Chevron. It's over 250,000 barrels a day. And it's rock solid. I mean, it runs very well. We have the interfaces. Very low maintenance was done on it. Huge uptime. And this was the top side, in this case, it was Yokogawa. But we both, but again, it's like a lot of organizations. And again, with this system being quite large, you have the right hand doing your topside system, your left hand doing your subsea system, and they don't talk to each other very well. And so what happened is we went on, and some of the challenges was, of course, the interface documentation. So we had a lot of planning. So to give credit to both organizations, we set up several meetings, interface meetings, to basically define how we're going to handshake on things and what the data is going to look like. And we put a lot of effort as a subsea equipment vendor contractor to provide the MCS into putting all that data together. So we did that at an early stage. Folks from Topsides, Yokogawa, they flew over. We had the meeting. We discussed things. We thought we were on the same page. We exchanged the documents. Now, of course, it's very tedious because, here an Excel sheet with all your Modbus addresses, and then here are all your OPC data and the different types of data, integers, 32 bits, and some of them you have to swap the 16 bits, and some of them you don't. And so basically the amount of documentation that was exchanged, and of course it leaves a lot of room for error when you're having to input those things on your side. So that was one of the first challenges that we had. Second challenge, of course, with protocols that we were used. I mean, OPC, DA had the baggage of Microsoft, DCOM, and then messages going over firewalls, and then once if the link gets broken, doesn't reconnect, things like that. And then you had the Modbus TCP with all the tedious, pack the data, unpack the data. Okay, and the third challenge was, of course, the integration testing. And so once we were done, so the detail for you guys, we were about to complete our in-house FAT and getting ready for the integration testing with Topsides. And then we get a communication from Topsides that says, hey guys, we can't do this handshake portion for all the commands that we have to send. And we're like, okay, that's going to change everything we're doing. But again, they were so busy with all their scope, and by the time they started implementing it, they realized that the way we dictated how to do the handshake was going to put a big overhead on their system. So we're like, okay, well, we just finished our in-house FAT. We're like 3 weeks ago from finishing and to move into the testing. And we can change it. But then that invalidates all our testing, and we have to do it all over. Tell us what you want to do. So within the Chevron organization, they met and they discussed, and they said, no, you continue. You had it documented. You continue, finish your work, and then we will do the interface testing later, and they just have to redo their work and add additional hardware. So in this case, there were 2 separate panels for the DCS to interface with our subsea system. Now, given it's a large 54 well, but 2 panels of controllers, just hardware, space, only to interface with our subsea system. And again, it was originally 1, but they had to double the amount of hardware because of a small detail on the handshake of how to send commands, which was described, but again, by the time they got to it to try to test it, it was too late, so they ended up having to implement it the long way with a big overhead, which ended up with, of course, extra cost and everything. Now, that facility is a gold maker, so I think everybody forgot about that, once they started producing within a couple of months. So what that, so that's a project example, but there were so many of them in our industry that happened that way. And what that caused everybody to realize is that, hey, we are not giving this interface the respect it deserves, okay? You cannot just say, oh, just give me this, and we need to do something better. So the MDIS, which is MCS to DCS Interface Standards Group, JIP, got started. That was in 2010. I started in the group from the beginning. A couple of our operators, they insisted that we attend because we were big suppliers for them. They wanted to make sure we're part of it. And I had never worked with a JIP like that before. And to try to everybody to agree on, what protocol to use and how to do it, because naturally everybody's biased to what they're used to. Even, just, I'm used to it, I don't understand this. I would like to do it this way. So the JIP started, and basically it has a group of key operators, BP, Chevron, Exxon, the list, a lot of them, all key operators, international oil companies, all the main DCS vendors, all the subsea equipment vendors, and system integrators like W Industries. Those are the current members of the group. And of course, the objective of the group is to basically streamline this interface. It's like, we can't keep doing this every project and problems and project delays. We just can't afford to do it. So that was the objective of the group from 2010. So it took us a while to, so the first thing we wanted to do is, hey, let's identify what protocol do we need to use. So we established selection criteria and a list of industry standard protocols, and we started evaluating them. Okay, how important are these criteria for us? How important, then what are the strengths and weaknesses of all these protocols? So we had about, actually more like 10 protocols at the beginning. And within the group, we did some voting, we looked at it from a high level, and then we basically decided to narrow it down to 3 protocols, which was Ethernet IP, OPC UA, and Profinet. So those were the 3 protocols. And at that time, we hired, because, each group supporting its protocol will say, no, that's not true. We do this better. And people couldn't make a decision. We're like, okay, well, I've only used this. Are these better? I have no experience. So we decided to contract an independent test lab, and we explained the selection criteria for us, and we wanted them to test these protocols towards them and give us a ranking for how does each one of them perform to these requirements. And from reliability, how they handle cybersecurity, bandwidth, media, and then also another intangible there was basically like what's like the survey we send out to all the DCS vendors, subsea equipment vendors, okay, which one would you support? Which one do you like better as well? Because we wanted to get a buy-in. We didn't want to pick something people don't want to use. How it supports redundancy and et cetera. So at the end of it, after all the testing, OPC-UA was the protocol that we selected to go forward with. So that was just the beginning of it. That's just, okay, now we have a protocol. Now if you start telling everybody to use it, you're still going to have a lot of the problems. So what's important for us was for the group is to continue and to establish a companion specifications, so for any user to be able to follow it and to be able to deliver. So, so for some of the things that are in the companion specification is the architecture of the system. Just a simple block diagram, but again, this is your DCS equipment, you got to exchange the data, and your subsea. We had two architectures. This one here details this here, which is you got your DCS HMI controllers, and this is MDIS protocol and guidelines here. This is the MCS, and then subsea gateway, and then down to the subsea control module, subsea electronic modules. Here is a case where some operators, they like their MCS to be of the same brand as their DCS, which we call it the integrated solution. So in this case, the MCS controller and the DCS controllers is the same brand, so they will talk natively. If it's Yokogawa, then they will just talk Yokogawa's protocol. If it's Rockwell, they will talk Rockwell's protocol, etc. But we still need to talk to the subsea gateway, and that's where this one applies. Now, I've recently been approached by one of the operators that basically wants to eliminate this and go in and come up with their own electronics, put it in these subsea control modules, and then talk straight from the basically from the MCS down to the controller without having a gateway from the subsea equipment vendor. But that's not covered at this time by MDIS. But again, it's showing the industry was beginning to realize that, hey, we have another good protocol, and again, with the companion specification that it comes with, it's getting a lot of attention. Another thing that's defined in the companion specification is a definition of MDS objects for us. So for a subsea control system, you have valves, choke valve, your instrument, different flow meters, multi-phase flow meters that go on the subsea wells, digital instruments. You have to factor in fault and warning processing. There's some interlocks built into these objects, and in some cases you put in some aggregation. So what I wanted to give you out of this slide here, I'm using the valve object as an example. So this is a subsea valve. Typically, you click on, operator clicks on it, that's what he gets. However, one thing I wanted to highlight is quite the difference between a subsea valve and a topside valve. A topside valve, you have a solenoid and you have limit switches to confirm the position, it's open or closed. In subsea, we don't have limit switches all over the Christmas trees on each actuator. Otherwise, then you'll have wires all over it, and it's just not very reliable in subsea industry. So we depend on measuring the pressure on the function line from the subsea control module all the way to each of the actuators. We look at the flow. So the way we know if the valve moved or not is like 4 different things. One of them is confirmation from the subsea control module that it received our command to open or close. Number 2 is we look at the pressure buildup on that function line and make sure it meets within the bandwidth where we say it confirms open or closed. And third thing is we look at the flow, how many liters did it flow, and we know that actuator takes that much fluid. And then the fourth measurement is basically a profile of that valve when it opens or closes. So it's a lot of data all built into this object. So again, all that built into one compared to the different pieces that you have to pass through OPC or Modbus or however we did it before. So basically, and then you take a lot of these objects. So again, like I said, we do one for valves, one for chokes, etc. And then you can aggregate all these objects into one object for a tree. So this is a subsea Christmas tree that sits on top of the wellhead. And these are all it shows all the actuators. So this is, you see how many valves there are that you have to operate on a subsea tree. This is a choke, and then you can see the amount of sensors that you also have to monitor. So you aggregate all these objects that we built, and you have one big object that represents the full well. Some of the other great things about the companion spec, it also defines the exchange of configuration. So if I am the subsea equipment vendor, I am the server. So once we complete the configuration, we would basically generate what's called a node set file, which is an XML format, and then that gets given to the client application, and they import it, and that's what gets used. So if you remember at the beginning, I showed you where you have a small time to, by the time the product is finished on the in the MCS side, and then to integrate into Topsides. So with this utility, which is clarified and described clearly in the companion specification, it makes sure that whoever says that their solution is compliant, that they're able to do this and to build in this feature. And we have validation and certification. That's also part of it. So we have profiles, grouping of functionality, we have test case definitions, and lab certifications that OPC would do. And they'll test all the interfaces, handshake between the two systems. So the standard has been released. It was released in early 2017. And now a lot of operators are beginning to apply it. And we're using it right now in one of our projects. Unfortunately, I cannot disclose the name of it, but it's a very large system. It's a typical deep water facility. Like I said, it's probably around 4,000 I/O points, just to give you a feel for it. In this case, it's 8,000 I/O points with an expansion module that could be added to it, which is going to put it above 10,000 I/O points. So it's a quite large facility. That's direct instruments tied into the process control and safety system. Again, I showed you that earlier. This is, again, typical architecture, and then you have this subsea interface. So in this case, up to 10,000 I/O points with the expansion module, and then there are 35 OEM packages that we have to interface with, and one of them is the subsea control system. So we actually, we've learned never to underestimate the value of interface management. I mean, it's very important to do some unit-level testing interface. So we actually have one of our engineers flying to different locations around the world to test those interfaces with each of the OEMs for each of the different packages. And these are things we discussed with the operator from the beginning to make sure we don't have any hiccups or setbacks or some misalignment between people. But when it came to the subsea interface, in this case, and the operator was not part of MDS. They didn't know anything about it. So they had specified something different. And at the beginning, when you're bidding, you just try not to raise any red flags. So we said, okay, bid compliant, we will do what you want. But once we got the PO and we're discussing it, we said, hey, we know the subsea equipment vendor. I mean, they're all involved in it, and we have this new standard that we have all tested together, and we've tested our interfaces, and we're both sides are very comfortable with it. So the operator, they were like, does it cost more? We're like, no. So that was our first project. We said, okay, the client agreed to change the specifications to it. And I think one of the greatest values is, this is a quick simplified architecture for the interface, and basically it shows just a simplified architecture as far as the interface between the MCS and the Topsides. But I think one of the biggest values of this is it has really significantly minimized the interface management by the operator. And they've really been like, they just left it because it's basically, we have all the specifications defined between MDS and then by basically the node set file that we would receive from the subsea equipment vendor. And on both sides, we're all on the same page. So it's that, and at the same time with all the objects and data models, that's going to simplify all the testing compared to the tedious. You have to check point by point because using Modbus, you're packing data, you're unpacking data. You have to make sure every single piece of it is validated. But here with these models, it minimizes a lot of the testing. And so overall, I mean, it's just, I think, although we said no refund for using OPC UA for the interface or MDIS, but overall I believe the client saved a lot of money with reducing their interface management effort and in the testing time from all parties. So that's all I had for you guys, and I know we're doing questions at the end, so my buddy Paul here will take care of you guys. He knows everything, so thank you.